let's begin. So we'll be talking more about this Schrieg topology. But it's been a little while since we've last met, and so maybe I'll start with a recap. So recall, well, let me start at the very beginning. So we have this category analytic rings, and objects in here are pairs. There's different choices about exactly what sort of data you want to put in the second piece. I'll take the sort of full derived category instead of some connective derived category or some abelian category, where this is a condensed. And in general, we want to say animated ring. So we're allowed to have some derived phenomena. And this is a certain full subcategory of what you could call D of R triangle, which is R triangle modules in derived condensed abelian groups, satisfying certain nice closure axioms for this inside there, which I won't recall right now. And then we define sort of the category of affine spaces to just be the opposite category. And we singled out three, I guess, classes of morphisms of affine spaces. So f from x to y in aff is so proper if so the pullback map from dy to dx. So let me define D on the level of aff by composing with this equivalence and taking the D on the ring there. If this has a good right adjoint, F lower star, where good means the right adjoint commutes with pullbacks. So if you do the right adjoint here and you pull back to some D of x prime, that's the same as pulling back to D of y prime and then doing the right adjoint there. But it also means that it commutes with colimits, and it also means that it commutes with sort of the dx action by tensor product on each of these guys here. Or the dy, sorry. I think I messed it up because this is, sorry. We have y prime. Well, yeah. Right, good means commutes with pullback. Yeah. Commutes with colimits. And satisfies projection formula, yeah.
Well, it's not exactly the case. The projection formula also functions in the other direction, but it is.
Well, okay. So there's a map in one direction, and you ask it to be an isomorphism. I mean, I don't know.
So you tensor with something in D of the...
In D of y, yeah, the base, yeah.
Which is then pulled back into D of x by the factor.
Yeah.
And then the F... okay, the right... Okay, so this is projection. Excuse me, it is like the projection formula, exactly. Okay.
Yeah. And the pullback, the kind of pullback I mean is like x, y, and then y prime, and then x prime. Just to, okay, and that was basically the same thing as saying the analytic ring structure is not really changing when you go from y to x. It's just the underlying ring that's changing. So you inherit the analytic ring structure from y when you go from y to x. So it's the same thing as the induced analytic ring structure. It was called an open immersion.
Induced where? On X?
Right. So this is implicitly given by a map of analytic rings from like I don't know, let's say S to R. So you're given an analytic ring structure here, and you want the analytic ring structure on here to be just inherited from this one, in the sense that the D of R is just the same thing as R triangle modules in D of S.
So D of R is also the subset of D of R triangle. Well, its objects after isomorphism are those which, when you restrict to S, are.
Yes.
Okay.
Exactly. Yeah. So it looks basically like an affine map in usual algebraic geometry, kind of, but we call it proper because of this situation here. So it's an open immersion if f upper star d of y to d of x is a localization and has a good left adjoint. Where good is taken in the exact same sense as before. The maps maybe go in different directions because it's a left adjoint instead of a right adjoint, but you can still always ask them to be isomorphisms. And this was equivalent to localize away from some idempotent algebra. In D of y. So such a open immersion, for such an open immersion, there's always going to be some idempotent algebra in D of y, which is somehow functions on the closed complement, which completely determines this situation here. As the kernel of this localization will just be the modules over that idempotent algebra. So let's say if this is A, so the sense of this is that kernel of upper star is just mod A, D of y. Okay, and then it was called shriekable if it factors as x bar y, where this is proper and this is an open immersion. And then there are good closure properties for all three classes of maps. So closed under composition, closed under base change, contains all isomorphisms, and this kind of half of the 2 out of 3, or 2/3 of the 2 out of 3 properties. So, so if you have a map like this and a map like this, and they're both shriekable, then any map between them making the triangle commute is also shriekable. And then, we get a 6-functor formalism. On AF, where the class of maps for which the important functor, the lower shriek functor, for which this is defined, is exactly the class of shriekable maps. And then F lower shriek is F lower star for F proper, and F lower shriek equals left adjoint to F lower star if F is an open immersion. Or another way of saying this is that F upper shriek equals F upper star. So that's just if you pass to right adjoints, I think, yeah, should be.
A map from F lower shriek to F lower star in general, or it's
Yes, there is. So this can be gotten because the or wait, just a sec. No, maybe not. Maybe not exactly in this full generality. Oh wait. No, there is. Yeah. I think it even just follows from. So you have such a map for an open immersion, because it's for any localization you have that kind of thing where like the left adjoint maps by a natural transformation to the right adjoint, and then you can just compose.
And then you have to show it's independent of the factorization.
Yeah, there's a better way to.
Is the higher thing needed?
No. Yeah, there's a better way to produce it, which involves using the diagonal. So, if you pass to the diagonal, it's enough to show that you have such a thing for the diagonal. Well, I think we'll get into this a little bit more later.
I missed when I was away because the closure properties are composition.
Yes.
And what else? And
composition and base change, they contain each of them contains all isomorphisms, and then there's this property that if you have two maps with the same target, which are in one of those classes, then any map between them is also
any map between two such guys is
also in the same class. Or I could say that the classes are closed under passage to diagonals.
This is equivalent?
Yeah. Once you have closure under base change, I think this is some basic thing.
Okay, passage to diagonal. But this is intuitively for an open immersion in usual algebraic geometry, the diagonal is an isomorphism.
Yes.
Also here.
Yes. Yes, also here. Yeah. Yeah. So that's part of why. So that goes into the other way of producing the natural transformation, but never mind. Yeah. Okay. So. Right, and then we had this definition, or we had this result. So we had this theorem, or maybe I should say definition. I'll say a map f x to y, let's say a shriekable map in F is a shriek cover if if the map from d of y to the to the limit of to the limit of the check nerve is an equivalence where for the transition functors we use the upper shriek functors. Which is a bit of a strange thing to do at first glance. But then we had this result that, so for shriekable F, the following are equivalent. So one is that F is a shriek cover. So in that sense. too is that we have kind of Schriek codescent. So if you take the colimit over n in delta op of d of x plus y n, so then here you use the lower Schriek functors and take the colimit in this category PRL, or in modules over d of y PRL. Then you get an equivalence.
So you had O in. So PRL is what you said that Lurie introduced.
Yes.
Presentable infinity category with colimit preserving factors.
Yes.
Okay, but not stable any.
No, but I could also say, oh darn, but the colimits, yeah, the colimits are going to be the same, so it doesn't matter.
Okay,
So,
and then mod d of y means PRL means.
it means, yeah, so d of y is a symmetric monoidal category, and it's in fact a presentably symmetric monoidal category, so the tensor product commutes with colimits in each variable, which makes it a commutative algebra object in PRL with respect to Lurie's tensor product, and then you consider modules. So it's a presentable infinity category which is tensored over d of y in a kind of colimit preserving way. And then the third condition was, so Schriek cover meant you have this Schriek descent where you use this funny twisted pullback. But it turns out that it implies that you get descent with the star pullback as well, and in fact it implies you get the same result with coefficients. So for all m in mod d of y PRL, so here.
You should take because you said can be both sides. Okay.
Where am I? There. So if you take m to be d of y itself, then you see that this condition is just kind of usual descent, that is descent with respect to pullbacks, star pullbacks. But in fact, you can even tensor that with any module and you still have descent. And then the fourth condition was this kind of two descent, this categorified version, which says that the whole category of possible m's satisfies descent. So, and here there's the only thing that makes sense is star descent, but I'll emphasize it. It's just some naive pullback. So where the base change functors are just kind of relative tensor products in PRL.
So one can ask, I don't know if it is a good question, but instead of just like in algebraic geometry, usually they define like MPQC topology using quasi-compact, but you can also ask, suppose you have an arbitrary collection of maps, not necessarily finite, you can ask whether you have descent for this. Can it happen within the infinite, which is not reduced to a...
We think maybe, I don't know if Peter checked the details. We think that it's true that, so you could try to make an analogous, we haven't talked about the Grothendieck topology yet, so but we're making it finitary by definition. But you could ask whether, if you do the infinitary analog of it, whether it reduces, it gives you the same Grothendieck topology as if, whether that Grothendieck topology a priori infinitary is actually finitary. And we think, yeah, so Peter, you checked it carefully? Yeah, okay, so then the answer is yes. If you could try to make an infinitary version of the Grothendieck topology I'm about to describe, and it will end up being finitary anyway. So, yes, yes. So every cover will have a finite subcover. The basic.
So I remember that in the case of just what we started with of finite sets, if you have the Cantor set and you take all maps on P to the Cantor set, which is a big, then this is universally submersive. Still, one can show it universally submersive.
What does that mean?
So there is this, like in the H topology, in the usual Vovodsky thing with the H. Anyway, it means that when you cross with any topological space to check if something is open, you can check the pullback.
Oh, right. Yeah.
So I don't know. Then of course you can ask whether you have the same tal cohomology or.
Right.
Yeah, this is not so clear. I mean,
No,
but at least for opens, one can check it. I mean, even this universal sense. So this is a kind of a candidate for infinitary thing, but I don't know if it satisfies the cohomological thing.
No, I think Peter, you were you asked these logicians about this, right?
Yes.
Yeah, and they had some conclusion.
So it can happen that you have some profinite set and some infinitary covered by other profinite sets, which satisfies the descent into the rough category. At least in some models of set theory, for example.
Descent in R of the derived. Okay.
If you ask for the streak descent, then because this is kind of polar limit condition equivalently along the lower streaks, using this perspective, you can show that it is finitary. But it's really something that only works when you ask for streak descent, not for star descent.
So for star descent, it is possible, like the example that I gave of all maps from P to the Cantor set. Is it? Well, maybe it's a side question. I don't know.
I think the specific one they looked at was like you take a really big profinite set and then you take a union of like small ones, write it as a big union of small ones. Like, I think that's the specific one they looked at. I don't know if they looked at this one with P in the Cantor set, but yeah. Okay, I think we'll move on. So. Right. So yes. So those are the equivalent conditions for being a Schriek cover. In particular, you have some very nice descent properties for Schriek covers. But now the next thing I want to talk about is how can you check these conditions. So here's a little proposition. So, well, the first part I'll say, so let's start with f from x to y, a shrinkable map. The first claim is that if f is a Schriek cover, then a certain condition has to hold. So, so if you look at the image of the lower Schriek functor from d of x to d of y, so that's a certain full subcategory of here. Since this functor is not, in general, fully faithful, that image doesn't have to have any closure properties whatsoever. It doesn't have to be a stable subcategory or anything like that. But then you can take the thick subcategory generated by it. This means a close under just finitary operations like cones and retracts, shifts and retracts.
So and idempotent. Okay.
Yeah, and retracts. I count that as finitary. Then you get an a priori bigger category. You can ask whether it's the whole thing, or well, you can ask it's actually equivalent, you can ask whether it just contains the unit. So I'm writing one y for, maybe you would normally think of this as like structure sheaf of y. I mean the unit object in this symmetric monoidal category with respect to its tensor product. So the condition, again, is that this unit object can be written in a finitary manner in terms of things which are lower shrieked from d of x.
And can it be written in an infinitary manner?
An infinitary manner?
Yes, but because of the Schrick, because it's a Schrick cover, it follows or not?
Oh, you're saying, so you're saying if I say this condition but with infinitary, does it automatically imply the same condition but with finitary?
I don't know, what is the relation between those?
Yeah, so I think probably, I mean, this is maybe the key point in all this finitariness is that this is a compact object in d of y. So I think indeed it should be equivalent. Yeah, so maybe it's even better to say, or is it? Maybe it's, I don't know. Yeah, I guess it should be equivalent. Yeah. Sorry?
Okay, what's the sentence?
Oh yes. So if it's a Schrick cover, then you satisfy this condition. And then the second claim is that the converse holds provided f is either and then the first will be the proper, provided, well, let me say provided either. One is that f is proper, and b, f is, I guess, what you could call universally locally acyclic. Let me explain what that means. So that means that f upper Schrick is good. So again, good means commutes with pullback. Commutes with colimits. And then, well, projection formula. But really the way to think about the projection formula is it's giving some d of y linearity, and it's that condition that you want to ask. So, which translates into saying that f upper Schrick should always be the same as f upper Schrick of the unit tensor f upper star. So tensor in d of x. So there's always going to be a natural map, and you want it to be an isomorphism. Yeah. Okay.
So all those properties of f upper Schrick are not true in general, and they are inequivalent, or they are, when you say good, is the conjunction of all of this,
yes.
And all of them are, there are cases where some of them are whole and the others don't. Or
that's a good question. There may be some non-trivial implications. Maybe if you, yeah, there may be some non-trivial implications here. I think, yeah,
Projection formula should imply that commutes with colimits.
Yeah, that's true. That's a trivial implication. Yeah, thanks. Yeah.
projection formula and
Peter is saying the projection formula clearly implies that it commutes with colimits, so I didn't need to write the second one, but yeah, okay. So I mean, how to think about this ULA condition? I mean, this is kind of like the dualizing object here, and the main claim is that the dualizing object is compatible with pullback. So if you're thinking of f from x to y as some family, then it's saying that the dualizing objects kind of very nicely in the family. So it's kind of some kind of equisingularity property for f from x to y. Okay.
Is there an example when the converse does not hold?
Oh yeah, so warning, converse fails in general. So let me give the example, which will explain kind of how you should think about this condition. So we could take, for example, so y to be spec, so let's say solid z bracket t z, and then take x to be x1 disjoint union x2, where x1 is spec, so spec of solid zt, or maybe I'll write it as u union z. So I'm gonna write, it's gonna be, I take a space and I take an open subset and its closed complement. That's gonna be the counterexample. So solid zt sitting inside solid ztz will be u, and then this is the complementary guy. So this will be solid z Laurent series T inverse spec. So spec is just this formal notation for passing to the opposite category. So f, so it's called, so this is mapping there by j, this is mapping there by I, and that induces a map from the disjoint union. Then j lower shriek of the unit is this sort of compactly supported thing. So it's the fiber of the homotopy fiber of zt going to z Laurent series T inverse. But I lower star, well, I lower shriek of the unit there, I is proper. It's a kind of a closed immersion. So this thing just gives z Laurent series T inverse. And it's clear that you can build z of t from this fiber and this guy by just one cofiber sequence. And then the lower shriek from x, the disjoint union, will just be given by restrict to u, take the lower shriek there, and restrict to z, take the lower star, take the lower star there, and then take the direct sum of those two objects. So you'll get this guy direct sum this guy. Therefore, by closure under retracts, if you allow closure under retracts, you get each of them, and then you get zt individually. So
when it is not shriekable.
Sorry?
You said it is not shriekable.
No, it's shriekable. Sorry? No, it's not. It's not a shriek cover.
It is not a shriek cover because for the cover you just get u and z separately somehow.
Yeah.
You get the derived of u across the derived of z. It's not the derived of y.
Exactly. Yeah.
Because here you have some x or something that is not the same in x and then y you could direct some z.
Yes.
Some particular common.
Yeah. Or I mean the ring of global sections on the disjoint union is kind of, it's the product of the two rings. Whereas, So yeah. Okay. So this condition is something like just set surjectivity on underlying sets, or maybe it's like a cover in some constructible topology or something. That could be how you think about this. And then if you want to go from that to some honest descent, you need to assume some properties. So this is analogous to like in maybe in topological spaces. If you want, there's descent for open covers obviously in topological spaces, but there's also descent for say finite closed covers, where there's like proper descent. But you can't mix open and closed and still expect to get descent. So that's kind of, yeah. So this is kind of some cover condition, some sort of set theoretic cover condition, and then if you assume either that you're some generalization of open, which is this ULA, or some generalization of closed, which is this proper, then you get honest descent. But you can't mix them.
So what is the relation of this? Like when we now go to like Huber's analytic spaces, where
Yes,
there are
yes.
certain topologies, like the V topology or the R topology,
Right.
that had some descent properties there. And what is the relation with the your notions here?
I'm not sure that I understand the precise sense of your question, but we will discuss, I will get to discussing Huber stuff in relation to these definitions later in the lecture. So let's postpone. Okay, right, okay. So the proof, so let's make explicit what this Schrieg descent according to the definition means. So we're using these upper Schrieg functors. Those upper Schrieg functors are right adjoints, and their left adjoint is the lower Schrieg functor. And there's some category theory which tells you that this comparison functor this itself will then also have a left adjoint. Which is given by sort of informally, so you have some collection of objects. And what you do is you take their you take a colimit in this category D of y, of the G lower Schriegs of them. Okay, one has to make this precise. I believe Lurie has done it, but that's the gist of it. So in particular for fully faithfulness, this amounts to the claim that if you take the colimit, and by G I mean for every n in delta, you have the map from this fiber product down to all the way down to y, and I'm calling that map G. I mean, it kind of depends on n, but it's just, yeah. So the colimit of these G lower Schrieg, G upper Schrieg m's mapping to m. So this should be an isomorphism in D of y for all m in D of y. So if you take m to be the unit in y, so this is a geometric realization. It's a colimit over this delta op, but you can filter that. You can always write this as a colimit over the natural numbers, and then kind of a partial totalization. So like, or maybe I'll say d, and then so n in delta op, where you restrict the cardinalities to be less than or equal to d. And this is a finite colimit. That's a nice fact about the simplex category. But then since the unit object is compact, if you write it as a filtered colimit of something, huh? Sorry? Where are we?
In delta, you wrote delta, what is the sub,
Oh, here?
delta op?
Yeah, delta op, and then I write less than or equal to d, meaning I'm looking at non-empty finite sets of, non-empty totally ordered sets of cardinality less than or equal to d. Yeah. Since unit y is compact, so that's the key property here, we deduce that unit y is a retract of some partial totalization. Where are we? But each of these lies in the image of f lower Schriek from d of x to d of y. Because all of these structure maps G from these fiber products, iterated fiber products, they all factor through d of y, or d of x, sorry, mapping to d of y. And as mentioned before, this is equivalent to a finite colimit, this partial geometric realization.
What do you mean by a finite colimit? A colimit over a finite usual category?
No, it means over a finite, say, simplicial set. So over a finite colimit over a finite simplicial set, kind of in Lurie's. It means it can be expressed in terms of iterated push-outs and, yeah, iterated push-outs and the empty and the initial object. So. Push-outs, yeah.
Here it is a colimit over a usual category,
Yes.
over a one category.
Yeah.
That is just the finite I forgot which one. The delta is a category of opposite of finite ordered set.
The simplicial objects are functors from delta op, so whatever that, so, I mean, yeah.
Okay, so this is.
I mean, in this stable setting, it's so the difference between this for D and this for D minus 1 is just given by one of these objects up to a shift, or maybe some, like, there's. I mean, the cofiber of the map, so we have a D-indexed system here, and if you look at the successive cofibers, then they're just described in terms of these individual objects here. So that's, I mean, in the stable setting, some kind of Dold-Kahn thing simplifies all of this. Yeah.
And so a finite colimit is defined in higher topos or theory?
Yeah.
So this is not more general than colimit over a usual.
Well, no. You have to be a bit careful because if you have a finite category in the usual sense, it might not be finite considered as a infinity category, or say considered as a simplicial set. So, for example, like the category with one object and like a finite group worth of automorphisms is a finite category in the usual sense, but it's not finite as an infinity category. Well, for example, because there's group homology in arbitrarily high degrees, so it's not finite. It's not finite as a simplicial set, BG. BG is not finite as a simplicial set. You need infinitely many simplices to describe it. So that's but this one's okay.
Okay, so you don't say exactly what. Okay.
Yeah. Okay. Right. So. Where are we now? Oh, so that was the implication, and that was part 1. So that proves part 1, and then for part 2, well, so For part 2, you can note that the hypothesis implies that every m are generated by things in the image of F lower streak. Because we have the projection formula for lower shriek, so you can just tensor this statement with m, and you'll get the desired statement for arbitrary m. So then we want to deduce at least the fully faithfulness, this we can assume by this claim here, we can assume that actually n is of the form F lower shriek n. And then if we have a base change result for commuting F lower shriek and say like, or let me say some like G prime lower shriek and G upper shriek, then we can reduce to a split situation. G, so yeah, I'm sorry, but it's not good notation. But so G depends on n. So G is just my arbitrary notation for one of these maps from projection maps from X tends over yn to y. So G is always going to denote like some structure map back to y. That's,
I'm now completely. Do you know projection formula for F lower shriek is part of the notion? I now don't remember.
I'm sorry. Yes. So it's part of the definition of what it means to have a six-functor formalism. So it comes from the fact that we assumed F to be shriekable.
Okay, and then you want to know that the limit of, but I think that it was not this, it was G lower shriek, G upper shriek M, or you want to represent.
Oh, I'm sorry. Thank you. Yes, I got them mixed up. Thank you very much. Yeah, I'm sorry. Yeah. And all of these maps G are like compositions of pullbacks of F. So if F has one of these two properties, then all of the maps G will as well. So in the proper case, so G lower shriek equals G lower star, and the base change follows from sort of the upper star lower shriek base change by passing to adjoints. And in the ULA case, we have sort of G upper shriek is G upper shriek of 1 tensor G upper star, and the base change follows kind of more directly from, again, the upper shriek lower star base change. So there is some, you have to make sure the two base change comparison maps that you're one, you know, a priori two different base change comparison maps, and you have to check they're equal, but okay. In order to conclude from one being an isomorphism that the other one also is, but okay. All right. So that proves fully faithfulness for 2. So that gives fully faithfulness. In the Schriek descent. But the essential surjectivity, or so the other adjoint, or the unit or the co-unit or whichever it is, the one going from here to there and then back up here again, that's proved in the same way. So handled similarly using base change to reduce to the situation where the cover is split. So you're pulling back to X where the cover is split. So we have a functor where we want to claim is an isomorphism. We've identified an adjoint to it. And what I've just explained is that if you do the functor and then the adjoint, that's the identity. And you'd also need to check that if you do the adjoint and then the functor, you get the identity. And I'm claiming that's handled similarly using base change along X going to Y, where it happens for formal reasons because the cover is split.
So when you are upstairs and go downstairs, then you want to reduce the kind of a split cover so it's even easier, but you still need some base change.
Yes, exactly. You need the same base change property, that the upper Schriek commutes with the lower Schriek for the relevant class of maps. Okay, so we're part of the way towards, so now we've, this is kind of a more concrete thing that you might hope to be able to check. So you have to be in one of these two situations. Let me explain some special cases. So special cases. So one will be closed covers. I should say maybe finite closed covers. So we defined a notion of a proper map, and we defined the notion of open immersion, but we didn't define the notion of closed immersion. If f is proper, and one way of saying it is that the pullback from dy to dx is a localization. Oh yes, it means the right adjoint which exists. The right adjoint is fully faithful. Nothing more.
No, but a localization in category theory, or in which context is defined now? For categories of which kind of, I forgot, I know that people like in Gabriel, and so I had some notion of localization, I don't remember now what are the contexts.
So let me say that, so this is a functor which admits a right adjoint. So when the right adjoint is fully faithful, which is what I'm calling localization, It follows that you have a universal property for colimit preserving functors out of here. Namely, they're the same thing as colimit preserving functors out of here, which kill every object, or sorry, which invert every map which is sent to an isomorphism by this functor. So.
So this is an analog of localization for triangulated categories, for example.
Yeah. Yeah.
Okay. And there is also like localization for usual abelian categories by.
Oh.
But okay, but then it's again the similar thing. But at least for Grodin categories and things which are closed, and I'm not sure in which depends if you assume that all colimits or all or not, or it's. No, I remember that in some old literature on category theory, there was something that the family, it looked very hard to read. And
No, I don't know. So when you have these big categories, the simplest thing to say is definitely just that the right adjoint is fully faithful. So, and that's what I mean by localization. Or the other, some unit map is an isomorphism or whatever. Yeah. Okay, but so since we already know that f is proper, which means that all of d of x, so this means that d of x is just modules over, so the push forward of 1x in d of y. That's the same thing as proper if you remember the discussion. So a proper map is just controlled by this single algebra object in d of y. So then being a closed immersion is the same thing as saying that this guy is idempotent. Algebra. So tensor product of two copies of itself in d of y is itself again via, say, the multiplication map. So this is since f is proper. So now let me make a warning. So in AF, so on the level of these aphanoids, it's not true in general, not generally true, that closed and open immersions, well, are in bijection. So say with the same target. So an open immersion is not necessarily going to have a closed complement. And a closed immersion is not necessarily going to have an open complement. It's close to being true that an open immersion has a closed complement. The only so let me expand on this. So given an open immersion, we get an idempotent algebra. So given an open immersion, so u to y, we get an idempotent algebra A in d of y, such that d of u equals d of y mod A d of y. But it's not true in general that A lives in D greater than or equal to 0 y. So it's not necessarily connective. And this is the condition. So this is the condition. This is the condition needed to get a closed immersion in F. So if you start with just an idempotent algebra, it doesn't necessarily correspond to a closed immersion in F, because it doesn't necessarily have a correct underlying animated ring. It's only the connective ones that correspond to animated rings, not the non-connective ones. So, yeah.
So in the case of usual schemes, can you recall what are the open, I forgot.
Well, it depends which functor from schemes. to analytic spaces you're using. So we'll go into it. But I want to say that this is analogous to kind of some complementary phenomenon in scheme theory, where, you know, for an affine scheme, you have a closed immersion. Then the open complement might not be affine, right? So it might not correspond to an open immersion in affine schemes, but it's still a scheme. And it's kind of similar here, even in situations where this is not connective. Usually you will get a closed complement, which is an analytic space. It just won't be an affine one.
But in the case of scheme, it's like you're taking the complement, like a U is a quasi-compact over in spec A.
Yeah.
Then you get R gamma U or U, which is idempotent.
Yeah.
But and does this correspond to in this setup to, like when you take D of A modulo this, what do you get? Do you get D of something which you call an open immersion? It's a closed right here, but not.
I'd rather, let me again get to the comparisons with the classical theories a bit later in the lecture, although this is going much slower than I anticipated. So I mean, I could give an example. So if you look at, so y equals solid z bracket, I don't know, two variables, x, y, comma, z, and then u to be solid. Then I invite you to do the very good exercise of figuring out what this idempotent algebra is, and then the corresponding A has a non-zero h minus 1. The situation on the other side is somehow even worse. So given in a closed immersion, well, actually, Peter described the condition required for there to be a complementary open. So a closed immersion corresponds to an idempotent algebra in the greater than or equal to 0 derived category of y. So closed immersion, say z to y. So then you need to get a complementary open in AF, you need that R HOM from the fiber of a unit of y going to A to this, which is a functor from d of y to d of y, you need this commutes with filtered colimits and preserves d greater than or equal to 0 y. So that's the formula for what would be the localization functor to the complementary open. And you need that actually defines an analytic ring structure in our sense, which amounts to these conditions here. Internal R-HOM, I should say. Yeah. Okay. Right. So as I said, some of this will be fixed by allowing general analytic spaces, not necessarily affinoid, but it's probably good to keep all this in mind. Maybe I should explicitly write that. These subtleties will be, to a large extent, fixed by allowing arbitrary analytic spaces. Or stacks, and not necessarily affine. Okay. Oh, sorry, I actually didn't plan to talk about this. But then it occurred to me I should. So yeah, I was talking about finite closed covers, right, as an example of descent. Suppose given finitely many, so Z1, Zn, closed subsets, closed immersions, well, with closed immersions into X. And all of these are in AF. So when do we get a cover? Then disjoint union of Zi mapping to X. So it's is a cover if and only if you just plain have the most naive form of descent for the structure sheaf. So and this is actually going to terminate at a finite stage because it's a finite closed cover. So this is the condition that i.e. the structure sheaf is a sheaf, so to speak. Well, yeah. Just so this is the idempotent algebra picking out Zi, and then this will be the tensor product of the two of them. So that's what I mean by that defines a closed immersion, which is the fiber product in the category of analytic spaces, or sorry, in fiber product in AF, that's what this is. So maybe by definition this is the fiber product in AF, but then it's also a closed immersion, and it's exactly corresponding to the idempotent algebra given by tensoring these two things together. So why is this true, that this is the criterion for being a Schritt cover? Well, if this is satisfied, then certainly 1 is in the image of the lower star functors from the disjoint unions of the Zi's, because each of these things is. So in this case, lower Schritt is lower star because the maps are proper. So we get this condition, but then that map is proper, so that implies a Schritt descent. Which is the condition that it be a Schritt cover. On the other hand, Schritt descent implies all this fancy star descent, right? In particular, it implies star descent for like d of blank. So d of x is the limit. And then if you just plug in the unit object in d of x and see what that base change and then the right adjoint is telling you, it's exactly giving this sort of structure sheaf being a sheaf condition. So yeah. So this follows from proposition. And this follows from star descent, which is implied by Schritt descent. Okay. Okay, what about open covers? Um, well, yeah, I guess. Yeah, so well, let me just say, so it turns out that every open cover has a finite refinement, if you say what it means to have an arbitrary open cover. But let me just stick to the case of finite open covers. There's, in any case, no loss of generality. So let's say we have U1 up to UN, again, mapping to X by open immersions. And let's say that U1 corresponds to, so the complementary closed is described by this idempotent algebra A1 and AN, sorry. So these are idempotent in D of X. Then intuitively speaking, these open subsets should form a cover of X if, when you take the intersection of all these guys, you get the empty set. Or intersection of all the corresponding closed subsets, complements, you get the empty set. So the claim is that disjoint union of UI mapping to X is a Schritt cover if and only if A1 tensor ... tensor AN is equal to 0 in D of X.
This is the case that the filtered colimit of idempotent algebra is 0 implies that one of them is.
Yeah, that's correct. And the reason is because the unit object is compact. So because an algebra is going to be 0 if and only if like 1 equals 0 in it. And then that's a question of maps from the unit object to your algebra. But if the unit is compact, then 1 equals 0 will be witnessed at a finite stage. That's the reason behind why an arbitrary open cover has a finite refinement. Yeah. Yeah. Okay. Right. Yeah, and well, let me just, for simplicity, so proof for simplicity, let's take n equals 2. You can kind of reduce to that case if you formulate the appropriate categorical analog of this. I mean, the union of two of these, U1 union U2 will not necessarily be an AF, so to speak. But if you formulate the appropriate, just purely categorical version of this statement, you can run an induction to reduce to the case n equals 2. So when n equals 2, then Schritt descent, well, so we need, right, so star descent, again, gives that, or how do I want to say this? So if you look at what star descent means and use the formula for the upper star functor, which is this kind of localization formula, then you find that the claim of star descent is exactly the claim that you have a pullback of this form. Wait, I'm sorry, I'm getting myself awfully confused right now. No, I'm getting myself very confused. This is the star. No, this is the star descent for the closed complement. I'm sorry. I'm sorry. Oh.
So of course, if something is a module over A1 tensor AN, then it goes to 0 on the UIs.
Yes.
So it goes to 0 in each stage of the simplicial. So therefore it goes to 0 apparently in this limit in the infinity categorical, well, whatever. So you have some scale in, so if the condition is not satisfied, then there is a.
Yeah. So I apologize. I assumed I would be able to do this off the top of my head, and I didn't think about it carefully. This is so. I mean, maybe I should just say so. Well, okay. Maybe I should just say this. So the Schriek, let me say, so Schriek descent. So the Schriek descent for this cover, say where you have two elements and both of them are mapping by monomorphisms into X, then the descent, which a priori involves some check nerve, which is some infinite thing, it actually reduces to some Meyer-Via torus, as is kind of standard. So it's the same thing as so D of U1 intersect U2, D of U1, D of U2, or maybe I'll make the maps go the other way. And these are the upper Schriek maps, all of them. Okay, and that should be a pullback. And then, and then you can check, then you have the map functor from this to the pullback there, and again it has this left adjoint, so the claim for the unit gives that the unit of X receives an isomorphic map from, you take J1 lower Schriek of the unit on U2, or U1, sorry, of J1 upper Schriek unit. Okay. Sorry. Yeah. So I mean, you have some kind of Meyer-Via torus sequence like this. So this is a cofiber sequence. And then you have formulas for everything. So I apologize for not explaining this very well, but you have formulas for all of the functors involved. So in terms of the corresponding idempotent algebras. And I promise that if you work it out, then it's just going to amount to the condition that A1 tensor A2 is equal to 0, meaning that this condition will be directly equivalent when you write down what everything means to A1 tensor A2 equals 0. So that would be a consequence of Schriek descent. But on the other hand, if you have this, then you have this, and this proves that the unit is written in terms of lower Schrieks from your guy, and therefore by the proposition, you get Schriek descent as well. I should have mentioned open immersions are, so open immersions are ULA.
So J upper Schriek 1 is 1, yes? Is 1.
Yeah, that's true.
J upper Schriek is J upper well, for open immersion.
Yeah, that's right.
Okay,
yeah.
So you have, and the J lower Schriek of this, how is it given in terms of the algebra?
So the J lower Schriek of 1, so this term, for example, will be the fiber of the unit mapping to A1. Yeah. I mean, yeah, it is elementary, which is, then I made a mistake by therefore not preparing it, because I thought it would just, my chalk would do it, but yeah, I'm sorry for messing this up. Okay. So those were kind of special cases, but we haven't gotten completely concrete yet because, well, it's still in some kind of generality of closed covers and open covers and so on. But now let's give some examples. So the first example is Zariski covers. So note that there is a functor from the usual category of commutative rings to the category of analytic rings, which sends a commutative ring to the pair. So we take R. Now we're viewing R as a condensed ring, but it's just discrete. So it has the discrete topology. And then we're actually going to take the full derived category of R. But now for emphasis, since this is just a discrete ring, I want to make sure we remember that we're taking the category of condensed R modules, so quite large. No solid, no. We don't need to localize to solid Z. So yeah, we'll just take all condensed R modules. Okay, so this induces a functor from affine schemes to what I was calling AF, which is maybe affine analytic spaces, which is just the same functor but viewed on the level of opposite categories. And well, maybe a remark is that this functor commutes with fiber products. Commutes with finite limits, in fact. So it also sends the terminal object to the terminal object. Or in other words, yeah, relative tensor products in commutative rings are also relative tensor products in analytic rings. That follows from our discussion of relative tensor products in analytic rings. But then I want to say, moreover,
so the relative tensor product, I mean, not underived or...
Oh, shoot, yeah. Maybe I should say derived. So let's say animated, yeah.
Then we are much...
Yeah, thank you, Ofer, yeah.
So now you are, and then you are, then of course all this notion of dr is much more, much more.
So Zariski covers map to Schriek covers. But now it's occurring to me, I forgot to remind what this means. So sorry. Just a sec. Sorry. So note, we get a Grothendieck topology on F by saying that a sieve over X in F is a Schriek cover if it contains finitely many yi mapping to x. Now I've switched the roles of x and y from previously. Sorry about that. Well, maybe I'll just call this xi, such that finitely many shrinkable, such that disjoint union xi mapping to x f is a Schritt cover in the previous sense. So, and the key behind this, besides kind of obvious properties of finite disjoint unions, is that a Schritt, if you have a Schritt cover, then any base change is also a Schritt cover, which is a consequence of this discussion of colimits in PRL.
What did you say now? That
if you have a map which is a Schritt cover, then any pullback of it is also a Schritt cover. Or base change. Any base change of it is also a Schritt cover. Well, yeah, there's. It's basically because of the fact. Well, if you can think in terms of this colimit in PRL business, and then it's just because the base change functor on the level of mod d PRL, the base change functor just commutes with colimits. So if you have the condition there, then you base change, you get the condition there. It's a consequence of two facts. The first was this kind of Kunith formula for, like, if you have a base change in AF, then you have the d's of all of these, and the d of the base of the pullback is just the relative tensor product of the d's of the other three guys.
d of this is the tensor product, and this is, and then you have that the descent that you had you formulated it in a more general way where you have a category which is a module over and then you apply this somehow and check that the maps are the right ones.
Yeah.
Somehow.
Yes, exactly. Exactly. Yeah. Okay. So, right. So that's what I mean by the Zariski cover going to a Schritt cover. Well, I guess I just mean that if you take the, has a finite refinement, and you take the disjoint union, then that thing will be a Schritt cover. Right. So the proof is simple. Indeed, Zariski covers go to closed covers in the sense just discussed. So if you have a principal open in spec R, and it's given by inverting some element, and that inverting an element gives you an idempotent algebra. And that idempotent algebra defines a closed cover on the level of these guys. And then the condition we had to check is just usual Zariski descent.
No, why Zariski cover gives a closed cover?
So let's separate that out. The first claim is that if you have a principal open, then that goes to a closed immersion.
Now it is called a closed immersion rather than. Okay. So this. I remember this in a previous talk.
Yeah, I mean, there's a picture that I would like to draw. You see, when you're doing analytic geometry, you have more room. You have more room than in algebraic geometry because you have like nearby infinitesimals almost. I mean, so usually you think of like the locus where f equals 0 in algebraic geometry. Like you think you have the locus where f equals 0, and then the principal open is the complement of this. And then you think, okay, the locus where f equals 0, that's obviously a closed subset, so the complement should be an open subset, right? But it's a little bit of a lie because, this isn't really where the locus where f equals 0. It's kind of, could also be just the locus where f to the n is equal to 0 or something like this. So it's really, what you're really deleting is not the locus where f equals 0, but you're deleting kind of the whole formal neighborhood of that. And so then it requires some fuzz. And then I claim that what you should really think is that that fuzz is making this thing really behave more like an open subset. And that the Zariski open, it should really be thought of as closed, and it should have a boundary, some kind of tubular neighborhood. There should be like, so it should really be a closed subset, and then the formal neighborhood, usual formal neighborhood, is the open complement. That's the picture I would like to suggest. Yeah. And when you go to the solid world, then you can again have an open version of puncturing. So if you then you can name this boundary. Maybe it's something like Z Laurent series T base changed along ZT to R, where T goes to F, something like that. You can name the boundary, and then you can remove it. So it's going to be a closed subset, and you can remove it, and you get an open subset, and then you're back into usual way of thinking of having a Zariski open, but then it's not. You're.
So you take R tensor Z bracket T, and then Z Laurent T.
Yeah. So I'm saying once you move to the solid framework, then you can name this boundary here, which before was just heuristic, and its name is this. So that gives an idempotent algebra in D of R Z solid. Well, in fact, it's in D of R1 over F Z solid, and the complementary open is like D of R 1 over F, kind of Z1 over F, Z. So Z adjoined 1 over F, whatever. Z union 1 over F. Yeah. So if you decided to, I mean, there's two different ways you can embed schemes into adic spaces, right? One is based on sending on the level of rings to RZ, and the other is based on sending R to R comma R. And this is the one that I'm discussing right now, well, base change to solid Z. And there Zariski opens look closed, but if you use this one, that corresponds to always removing the boundaries, and then Zariski opens actually go to open immersions in the discussion. Yeah.
So what do you mean by boundary? Like the formal neighborhood minus the middle?
I don't know what I really mean by boundary if I don't just mean this formula, but intuitively I'm claiming you're removing kind of an open piece from this chunk, and then the closed complement should intuitively speaking have some boundary. I mean, there's going to be boundaries at infinity too if your thing isn't proper, and so I mean, there's what's happening at infinity is also important. But let's pretend we're in a proper thing or something. Okay. Other questions? Okay. So in particular, yeah, we get a functor from like Zariski sheaves on affine derived schemes to Schriek sheaves on F. which is in fact pullback of topoi. So, I mean, it commutes with colimits and finite limits. That's kind of a consequence of this. So this is one way of embedding usual algebraic geometry into, well, I haven't quite defined what an analytic space is. It's not exactly going to be this, but it's close enough for practical purposes. I mean, we're going to have some kind of hyperdescent condition we want to impose as well. I thought I was going to get to it today, but I'm clearly not. But this is basically analytic spaces, or analytic stacks, modulo a couple of technicalities.
So this is sheaves with values in simplicial set.
Right, so there's the question of, yeah, and that's related to whether I want to use hypersheaves or not. So I mean, we could do either. We could do sheaves with values in sets and just, yeah, well, why don't we, yeah, what I really will mean is sheaves with values in what Peter and I have been calling anima, which is what Lurie calls spaces, which is what other people call Kohn complexes, but the quasi-category of Kohn complexes. Some people call homotopy types. Yes. Something has many names. It's probably because it's a subtle concept. But, yeah. Well, anyway. Yeah.
It makes sense to look at just sheaves of sets when you have the derived thing, so.
I think it still makes sense, yeah.
It makes sense.
I think so, yeah.
And it makes sense to look at the n topos, like sheaves of truncated this makes sense.
Yeah, it makes sense.
And there the descent and hyperdescent are equivalent.
Yes, exactly.
Then when you go to to all Kohn complexes, then you have different, potentially different descent conditions.
Yes.
And when you write this, you use the weak one, which the check covers.
Yes. Although if you did a stronger one, you'd still get the same claim because it would be just a further localization of this. So.
And then on the other side also.
Yeah, well, right. So I'm not going to touch the other side. One could, but.
No, the risky sheaves.
Yeah.
Does it also depend on whether you have hyper?
Oh yes, it does. Yeah. But I'm not going to. On this side, I'm not going to care too much. But well.
And it was said in some talk, I don't remember who, that there, or maybe Peter Schulze said that there would be something intermediate between check descent and full hyper descent.
Correct. Yeah, I was going to discuss it today, but it's not going to happen. Yeah. Okay. So, and then the other subtlety is like set theoretic subtlety, because like the category of commutative rings is not small, so you have to be careful considering pre-sheaves and sheaves on it and so on. And same with.
Did you take only those which are accessible?
Yes, exactly. And then you have to prove sheafification preserves this accessibility and so on and so forth. But okay. I don't think in the remaining like 7 minutes I could do justice to the next topic was going to be adic spaces. I could rush through it right now, but I don't think that's a good idea. So I think I'll stop here.
Could you define Zariski covers here by some finite topology?
Well, I don't have to.
No, I wanted to know what's for example, ethyl covers is a Schwick cover.
Oh, sorry, I didn't understand your question. I'm sorry. Yeah, whether an étale cover also gives you a Schwick cover. Yes, it does. It does. Right. So this is. Thank you. I think maybe this is something I should do in a few minutes. So this was all. I mean, a lot of this was motivated. This was motivated by Akil Matthews' theory of descendability. We were talking in AF, right? And then we were saying we have this derived category of anything in AF, and it's built on this condensed framework. But it's clear that the discussion is very categorical in general. And we could just try to make the exact same definitions in the world of ordinary algebraic geometry instead, using like for a ring, you just have its usual derived category and see what the kind of definitions give. So if you take the same definitions, but with the pair R dr, so this is a usual commutative ring, or maybe derived, and then this is the usual derived category. So instead of analytic rings, we're just looking at commutative rings. Then some simplifications happen. First is that every map is proper. That's quite clear. Well, maybe that's the main simplification that happens, is every map is proper, because by definition, you know, if you have R mapping to S, then D of S, well, almost by definition, then D of S is just the same as S modules in D of R. So this implies that every map is shrinkable. And then the proposition that I discussed over here, there's no condensed thing here. Yeah.
What is the shrink? What's the upper shriek and lower shriek?
Oh yeah, so it's not what you might think. So the upper shriek is just the right adjoint to lower star, which exists for general categorical reasons. It's not the same as the upper shriek in Grothendieck duality theory. So caution. So for spec k bracket t going to spec k pi. So the pi upper shriek is not the usual one.
And pi lower shriek is what?
Pi lower shriek is just pi lower star. So that's what I mean by every map is proper.
Okay. So the lower upper shriek is like for finite map is the same.
Yeah.
One case.
For finite prime representation, I mean,
Yeah.
pseudo-coherent maps, it's the Grothendieck duality.
For proper maps, it's yeah. But for arbitrary maps, it's just some funny thing. Nonetheless, it turns out to be useful, exactly in this descendability discussion. Because so every map is shriekable, every map is proper, and then we deduce that so a shriek descendable, or a shriek cover, is the same thing as saying that so a shriek cover x to y is the same thing as saying the unit in y lies in the image of just so f lower star, d of x to d of y. And this is exactly descendability. This is the definition, descendability in Matthew's work. Or that's one equivalent. He gives many characterizations.
What about the classical Grothendieck FPQC descent? Is it related? What is it?
Let me give some examples. Actually kind of purely formally, any descendable map R to S in a Kiel sense gives a shriek cover in AF via this functor here.
Shriek cover in AF now in yours.
Yes, exactly. Yes. And Matthew gives many examples of descendable maps. So examples. So atoll covers. So that's more general than Zariski. But also more generally than that, countably presented faithfully flat maps. So FPQC covers. So this is kind of funny. You need this, well, we apparently, probably for real, need this countably presented hypothesis. Countably, that means that, so you have a map from A to B, which is faithfully flat, but also B is presented as an A algebra, or maybe even just countably generated is enough. So B has a presentation as an A algebra by countably many generators.
So here when you work with simplicial rings or animated, so the condition is that on pi 0 it is faithfully flat and that the pi I are this is kind.
I did not carefully think about, let me say for this I mean ordinary rings, because I didn't carefully think about the derived analog.
Sometimes they in some references they have this derived thing with faithfully flat where they define it like what I said.
Oh yeah, so it is true that
in that case you need to do it.
Yeah.
And then faithfully flat
ordinary rings.
Countably generated because you need to
maybe
there is some so it's equivalent to the kernel, the fiber tensor, it's the map from fiber to A. Here is some tensor power which is 0.
Yes.
And this is related to some limit, higher limit. I mean, so if it is a colimit of Aleph n things, which
that's fine too, but in practice it's the same thing. I mean,
but if it is only countably generated, then you don't get.
Maybe it has to be countably presented. Yeah, because you need to be able to reduce to a countable ring, a countable base ring. I'm sorry. Yeah, let's say countably presented. Anyway, the point is, a lot of situations where you have classical descent. You get this even stronger Schrieg descent, which recall gives also this 2 descent and much else besides. But also there's some, like if, so R going to R mod I, where I is a nilpotent ideal. And now you have to be very careful. Now these are ordinary rings, but the Schrieg descent is defined on the level of the derived categories. So the descent you get for this does not imply that D of R is the same as D of R mod I, obviously. And the reason is that you have, when you do the descent, you're doing everything on the derived level, and so it's you end up with terms like this in the colimit diagram, and that's not the same as R mod I.
What about R going to pi 0 R? Does it have the same property, R going to pi 0 R?
R going to pi 0 R, no, Peter says no.
And you can have a polynomial algebra in a degree 2 generator. And this has a module where you invert the degree 2 generator.
Yeah, that's right, yeah. So if you look at like, I don't know, Q bracket X, degree X equals 2, then there is a ring, a module in particular, where you invert that generator, which goes to 0 when you mod out by X, but is non-zero. So
what's the analog for simplicial ring of an nilpotent ideal?
You should ask that it be truncated, the ring be truncated. So it has only so you should ask that R has only finitely many homotopy groups, and then then going to pi 0 R mod I. Yes, so that's some kind of Artinian situation you could think. I don't know. Yeah, and so more generally, I think maybe Yeah, I don't know who proved it. But maybe it was Bot Schulze. But if you have like a proper map, I'm talking about the affine situation here. But okay, you can extend it to schemes. But if you have a proper map of Noetherian schemes, then you also get descendable. So that's a generalization of this here. A proper surjective map, yeah. Sorry. And more generally, H cover. I mean, that's kind of just a combination of this and that. Let's say finitely presented. And maybe I won't. Okay, so anyway, there's a huge class of very, very much. But you do have to remember in like cases like this and in non-flat cases, you do have to remember the descent involves a higher torus and so on. So yeah, all of these kinds of things will go to Schritt covers in our setting there. Okay, so now I'll really stop. Sorry for going over. Yeah.
So in these two versions, there's one is taking the classical one, and the other is two with condensed structures. That would not make a difference for seeing whether it's a Schritt cover or not.
Well, it's a priori possible that for some weird reason, well, is it? A priori, it's possible that for some weird reason you could have a map of commutative rings where you go into that world, it becomes a Schritt cover because of some weird condensed modules. I kind of would be surprised if it actually happened in practice, but I'm only claiming an implication that if you have a Schritt cover here, you get a Schritt cover there. Wait, no, it's just tensoring. Yeah, no, a priori it's possible. It's possible. It sounds very strange, but yeah, I don't know. The question was whether it's equivalent to have, if you have a map of commutative rings, whether it's equivalent for it to be descendable in the ordinary commutative algebra, a Kiel-Matthew sense, and whether the image under this functor is a Schrittable map, a Schritt cover in our sense. So,
I think it's equivalent.
Is it equivalent? So what's the argument?
Well, I mean, it's equivalent to descendability in this kind of relative sense, but this is just meaning that the descent, this mentions pro object is a pro isomorphism. But this pro object is just the old discrete pro object.
Well, wait, but yeah, okay. Yeah. Thanks. Yeah. So yeah, what Peter was pointing out is there's another characterization of descendability, which is in terms of, on the level of just the rings, like A, B, B tensor A, B, and so on, you get some, first of all, you have to have descent. You have to get a limit diagram, but then you have to get even more. You have to get a very stable limit diagram. It has to be a pro-isomorphism between the tower you get from this cosimplicial thing, the n-index tower, and that pro-object should be a pro-isomorphic to the constant pro-object A. And in that condition, it is clear that when you that it's independent of which framework you put it in, because the pro category, because the usual D of R sits fully faithfully inside D condensed R, and therefore pro of usual D of R sits fully faithfully inside pro of D condensed R. So yeah.
And so for the pro thing, it's enough to work in homotopy categories. It's enough to work in weaker.
For the pro thing, I mean, I don't know. So, but what you can do is you can pass to the fiber, and then you want to know about a tower being pro 0, and then it's enough to look in the homotopy category. Yeah. Okay, thank you again for your attention.
So when it is pro zero,
Yeah.
then is it the case that that it is uniformly pro zero? That is because there is some finite. Does it mean that
Yes.
it's enough for any stage? It's enough to add a fixed number
Exactly. Yes.
in Matthews.
Yes.
And it works. And he works with simplicial rings. So
He works in actually a very general setup, just like a commutative algebra object in PRL again. And then sometimes he specializes, but for the general discussion, yeah. But he only looks at the proper case. So for him, so he works with his base category is always some very general thing like C and C-alg PRL, a presentably symmetric monoidal thing. But he only ever then considers algebra objects in C, and he's comparing like C to mod AC, and he's talking about descendability kind of in this sense. So it's for him, every map is proper in our sense. So
in commutative algebra object is it like a symmetric monoidal category?
yeah,
And then you consider A is an algebra
yes. And then you take A and algebra in C.
So you work in this setup and then it defines descendability in this context.
Yeah.
Okay.
So it specializes also to the condensed world, but it's only discussing the proper maps, not the arbitrary shrinkable maps.
All right, see you, Dustin.
Yep, see you, Peter.
Can I ask you something about what you said last time?
Okay.
Oh, I think it was last time. They mentioned that we have this kind of decomposition.
Oh, yes, the Kuhn formula, yeah.
Kind of formula. And so it's probably not true that we have this for all analytic stacks, right?
Right.
But for like QCO, we have these class of perfect stacks.
Yes.
Do you have, I mean, it's a big question, but do you have a similar intuition for like class of objects for which this should?
Yeah, I think it should be pretty similar. Yeah.
Okay.
Yeah. This is something that will be relevant because we're going to talk about extending this. Right now we have a six-functor formalism on F, and we're going to talk about extending it to more general analytic stacks, and this kind of condition will show up again. Yeah. And I also didn't discuss like fully faithfulness of it's easy to settle here, but for more complicated situations, the fully faithfulness of some functor from classical analytic spaces to our analytic stacks is not at all easy to settle, but yeah, similar considerations have to come into that as well. The essential problem is that this Grothendieck topology is quite inexplicit. Like in usual Zariski or et al., you kind of have a good handle on the covers because they're finitely generated, for example, and you can kind of give standard models for what they look like. But in this setting, it's much more difficult to get control over the Grothendieck topology, so it's harder to a priori prove that locally something weird can't happen. But okay, yeah.